Hey everyone, today we're going to talk about oxygen carriage in the blood. This is a topic that I touched on briefly when I talked about oxygen delivery in a previous video, but in that video we focused on the equation for delivery and carriage. This time I'm going to show the practical elements to oxygen carriage and describe it in the context of hemoglobin, and also show you the oxygen dissociation curve and how it's manipulated in different states. So oxygen carriage, if you remember from my previous video, it can either be dissolved or carried on hemoglobin. And as we established, hemoglobin is the main way that it's carried. So in our blood, we've got biconcave erythrocytes, and they're also known as red blood cells. And they're in this shape because it allows them to fold and bend and get through capillaries, which is important later when we talk about sickle cell hemoglobin. So in each red blood cell, there's about 200 to 300 million molecules of hemoglobin. And on each of these molecules, there's 4 globin subunits, which are these complex folded proteins. And there's usually alpha 1, alpha 2, beta 1, beta 2, which I've represented here. And then in green, I've got these protoporphyrin rings, which contain an iron element in the ferrous state. And there's 1 per globin molecule or globin protein, so there's 4 in total per hemoglobin. So an interesting feature of hemoglobin is that as oxygen binds to one of these iron subunits, it causes a rotation or a shift or change within the protein of the next globin protein, which then leads to exposure of that iron subunit, meaning that more oxygen can bind, which then leads to more rotation and more binding and increased affinity for oxygen. So a deoxygenated hemoglobin sits within this state called a tense state, and the tense state, it's got a lower oxygen affinity. But then as an oxygen binds to each of these iron subunits, to the heme subunit, you then get rotation of the next globin protein, which then opens up the heme, meaning that more oxygen can bind, and then it becomes this relaxed state, which has increased affinity. And in the relaxed state, the affinity of hemoglobin is about 70 times more than the tense state. And this is important when we talk about the hemoglobin oxygen dissociation curve and its shape. So there's different types of hemoglobin, and I briefly already mentioned there's adult hemoglobin, which is 2 alpha, 2 beta globin proteins. And then there's fetal hemoglobin, which we have while we're in the uterus and for a few months after during neonatal life. And this fetal hemoglobin, rather than having beta subunits, it has gamma subunits. And these gamma subunits have more affinity for oxygen, which I'll talk about again later in this lecture. Then there's probably the med school sort of hemoglobin that we're aware of, which is sickle cell hemoglobin. And this is where the valine replaces glutamic acid as the 6th amino acid along the beta chain. So they still have 2 alpha and 2 beta, but the beta chain is slightly different, and it leads to less solubility when reduced, which means that the hemoglobin changes shape. And this is what sickling is, and why sickle cell anemia is worse when the person is hypoxic, because these deoxygenated hemoglobin misfold and they cause the shape of the red blood cell to change, and they form these sickle red blood cells, which are very fragile and they don't fit through capillary beds. And we mentioned before the biconcave shape of erythrocytes helps them fit through there. So rather than fit through there, they then block up the capillaries and you get sickle cell crisis. Lastly, there's methemoglobin. So methemoglobin is just where the ferric heme group is, rather than being in the ferrous state, it's in the ferric state. So already a positive ion attached, so it can't actually bind to more oxygen in this state, but it won't easily release the oxygen either. So it's this bound hemoglobin or bound heme that can't release oxygen. And then other important hemoglobin states or subtypes of variants that you should probably know about would be your thalassemia variants, which I won't talk about specifically in this video. So let's put this in the context of the hemoglobin oxygen dissociation curve. So you draw your normal graph, and then on the y-axis is saturations of hemoglobin with oxygen, And the important numbers to note is 100% at the top, 50% in the middle, and 75% between there. Then on your x-axis is partial pressure of oxygen, and this is in millimeters of mercury. And the important numbers here is 100, 40, and 26. So I'll draw your attention to the shape. So it's this sigmoid shape, and that's really important. And we'll talk about it more once we've got our important points on the oxygen dissociation curve. So the 3 points that we can mark here at the intersections is the arterial point, the venous point, and the P50. And then I'll just mention an extra axis that some graphs will mention, and it's the oxygen content, which is in mil oxygen per 100 ml of blood. And the important numbers to note here is just 20 mil per 100 and 15 mil per 100. For our important points, the arterial point is 100% sats at 100 millimeters of mercury, and this is about 20 mil of oxygen per 100 ml of blood. And this is arterial blood. So this is blood just as it passes through the lungs has been oxygenated and about to be distributed through the rest of the body. Then there's the venous point, and this represents venous blood. So this is blood that's passed through the muscle. It's just gone through the right ventricle and about to go through the lungs to be oxygenated. And this is at 75% oxygen or hemoglobin saturation at 40 millimeters of mercury of oxygen, 15 mil of oxygen per 100 ml of blood. And then the P50 is the point at which hemoglobin saturation is 50%. And in adult hemoglobin, this is at a partial pressure of oxygen of 26 millimeters of mercury. But the importance of the P50 is that it represents the affinity of the hemoglobin for oxygen. So let's go back to the shape of the oxygen saturation curve or the dissociation curve. And the shape's very important because it sort of represents the physiology of the hemoglobin and also has some implications to how we deliver oxygen as well to the tissue. So down at the lower left corner, this is deoxygenated hemoglobin. And as we mentioned before, it's got low affinity for oxygen. And then you can see as we move to the right, the steepness of the curve increases. And this is because, as we mentioned, there's a conformational change in the hemoglobin as oxygen binds and the affinity increases. And remember that between the tense state marked in T and the relaxed state marked in R, the affinity for oxygen is 70 times more. And this is why the curve, as oxygen binds to hemoglobin, rapidly increases in affinity and gets its shape where it suddenly goes very steep and then it will flatten out. And the flattening occurs as there is a finite amount of oxygen that can bind to hemoglobin, and it becomes harder and harder to bind beyond that 98% mark. You need to have a higher partial pressure. But once you go above about 100 millimeters of mercury, the binding of hemoglobin is, the change is very little. But then an important feature here is that as partial pressure drops, there's between probably 80 millimeters or 60 millimeters of mercury and 100 millimeters of mercury, the curve is quite flat and our sats remain quite high. And then it's sort of around the point of about 60 millimeters of mercury, which isn't marked on this graph, but it's the point where the curve starts to become the steepest, just above that venous point. That's where you'll get this sudden desat and drop. And this is why it's important to intervene earlier in hypoxia, because once you drop below a certain percentage, it becomes harder to recruit those hemoglobin and get your sats back up. And some textbooks will identify this 60 millimeter of mercury point, which represents about 92% sats or 90% sats, depending on the textbook you read, as the ICU point, as generally we'll aim for on an ABG, our PO2 to be greater than 60. So earlier I mentioned fetal hemoglobin, and if the P50 represents affinity for oxygen, the P50 for fetal hemoglobin is 19 millimeters of mercury, and this is compared to the 26 millimeters of mercury in adult hemoglobin. Hence, the affinity is much higher for oxygen. And the importance of this in fetal hemoglobin is that it allows fetal hemoglobin to essentially steal the oxygen from the mother's hemoglobin to be able to get oxygen to the fetus. So the last point we'll touch on, which is really important for the oxygen dissociation curve, is left shift and right shift. So left shift, marked in orange, we can see here, has a lower P50, which, as we already described with fetal hemoglobin, means that the affinity for oxygen is higher. And then right shift, the P50 is increased, meaning that there's decreased affinity for oxygen. So causes of a decreased P50, meaning increased affinity for oxygen, would be low CO2, low temperature, low hydrogen ions, which would lead to an increase in pH, and low 2,3-DPG, which is a byproduct of red blood cell metabolism. And I've marked here in brackets fetal hemoglobin because part of the reason why fetal hemoglobin has a increased affinity for oxygen or a decreased P50 is because the 2,3-DPG can't bind to the histidine groups on fetal hemoglobin and block the heme group from binding to oxygen. And then our right shift is essentially the exact opposite. So increased CO2, increased temperature, increased hydrogen ions with a decreased pH, and increased 2,3-DPG. So why is this important? Well, it's because the oxygen hemoglobin dissociation curve is not a static curve. It's actually a dynamic curve, and it changes in different parts of our body. So, for example, the left shift increases affinity for oxygen. And this would be a feature that we would want to occur, for example, if we wanted to take on more oxygen. And it probably wouldn't be a good idea for our body to do this if it was near muscle, because we want to offload oxygen when we're near muscle so the muscle can metabolize it. So the left shift represents the blood that's entering the lungs. So in the lungs, you have offloading of CO2. So you have decreased CO2 in the blood, and you have an increased affinity for oxygen, and you also have decreased temperature of blood in the lungs as well. So you're going to have more affinity for oxygen and more binding that occurs, which is an important feature and helps us make the binding of oxygen to hemoglobin more efficient in the lungs. Then in the muscle, where we want to offload oxygen, through metabolism of cells, we'll have increased CO2, we've got higher temperatures in the muscle, we'll also have more metabolism, more hydrogen ions, and more 2,3-DPG that's present as well. So this is a feature that's favorable to offloading oxygen at the level of the tissues in the muscle and binding to CO2. And this is known as the Bohr effect. So the Bohr effect is the effect that we see from the increased CO2, the increased temperature, and the increased hydrogen ions with the increased 2,3-DPG. And it's the effect that describes the increased oxygen offloading or the decreased affinity of hemoglobin for oxygen at the tissue levels. Now, our left shift in some textbooks will be referred to as the Haldane effect, but I just want to differentiate the Haldane effect here because the Haldane effect is more focused on CO2 carriage. The Haldane effect describes how oxygenation of hemoglobin in the lungs displaces carbon dioxide, increasing the removal of CO2 and facilitating its transport from the tissues to the lungs, effectively reducing the hemoglobin's ability to carry CO2, which I described further in my previous video about CO2 carriage in the blood. Because in some textbooks it will mention the Haldane effect as the left shift and the Bohr effect as the right shift. So that essentially describes the hemoglobin oxygen dissociation curve and how the blood carries oxygen. If there's any questions or any other topics you want me to cover, feel free to leave it in the comments and I'll happily go over it on my next video.